All right, this is problem 361 out of the textbook. Basically, you need to find the tension in each cable for equilibrium. So cables AC, AB, and AD, and then we have the 800 Newton force acting up. I did this problem before after a long day, and I had done multiple videos for this class and a lot of other things, and was not getting the right answer. So with these, you just have to be make sure you're really methodical in each step, because what it ended up being was just a negative sign, or one of the things should have been a negative instead of a positive. So you just have to be really careful with these problems. That's just a little warning. So for this problem, so I'm going to write in pink. We'll start with doing a free body diagram. That's what we usually do. So we'll do A, then we have that 800 Newton force acting up, and then we've got a force from A to D, one from A to B, and one from A to C. And in this, I really recommend that you look at the textbook and not at my drawing. I think that'll make it a little bit easier for you to see the different things that you're doing, or the different dimensions. My drawing may not be the best. You obviously want to draw that in your notes too, but look at the actual drawing in the book. So for us to figure out the tension in each of these cables, we know something about the direction, right? So they give us the dimensions. I think A is actually on that z-axis. It's 5 meters up. And then they give us stopper points B, C, and D. And we know we can use unit vectors because we have the direction of these. So basically, we know that if we're interested, let's see, I'm going to use a different color, and AB is going to equal that magnitude of AB, which is what we're interested in, so that tension at AB, times that unit vector from A to B. And that unit vector, so AB is going to equal AB times that position vector from A to B, divided by the length of that position vector. So AB is going to equal, and we don't know what AB is, the position vector from A to B. So how do we get from A to B? Basically, we're going to need to go down 5 in the z direction, so that would be minus 5k. In the x direction, so to get to point B, we're going to have to go positive. So from A to B, we go down the 5k. We're going to go positive 5 in the I direction, and positive 4 meters in the I direction, and then positive 4 meters in the y direction. So 4I plus 4J, and these are all in meters. So we'll check that. So we start at A. We want to go 4 in the I direction, so I'm just drawing along with my finger in the book, and then 4 in the J direction, and then down 5. So that works, and our units are all correct. And for me, actually, when I did it wrong, the units were correct in this part of the problem. Is when I went to the next page that I didn't draw it again. So you just have to be careful with these. So for the, and then we have to divide that by the square root of 4 squared plus 4 squared plus 5 squared. So the square root of each of those components squared. So AB ends up equaling, so the square root of 4 squared plus 4 squared, so that's 16 plus 16 is 32, and then plus 25, so that's 57, so that would be 4 over the square root of 57, I plus 4 over the square root of 57J minus 5 over the square root of 57K. And that's in meters. So now we'll do the same for AC. I would recommend actually just doing this on your own and then checking your work to see if it's the same as what I did. So I'm going to go to the next page. We have AC is going to, actually, let's undo that. Actually, I'm going to first just paste what we just found. Alright, so I just copied the AB over because we'll need that in a little bit. So now let's do AC. So that's going to equal that magnitude of AC times that times the unit vector. And so first we'll do the position vector from A to C. That's also going to be negative 5K because we need to go down 5 meters. And then we need to go 3 meters in the J direction and negative 2 meters in the I direction. So minus 2I and plus 3J and then minus the 5K. So I'm going to check that really quick. So we start at A, we go we go minus 2 in the I direction, plus 3 in the J direction, and minus 5 in the K direction. And then we're going to divide that by the square root of each of those component squares, so 2 squared plus 3 squared plus 5 squared. So we're going to get AC equals AC times, 4 plus 9 is 13, plus 25 is 38, so we get negative 2 over the square root of 38I plus 3 over the square root of 38J minus 5 over the square root of 38K. And that's meters. So now the last one we need is AD. So pick another color. So AD is going to equal the magnitude of AD times that unit vector. So we'll do the position vector. This is also minus 5K. That's meters. And then to get from A to D, we go minus 4 in the I direction. Minus 4, and then we go minus 5 in the J direction. And then we divide by the square root of those three. So 4 squared plus 5 squared plus 5 squared. So that's 25 plus 25 plus 16. So that's square root of 66. Pause for a second and check that. Alright, so I just checked to make sure the square root of it was right. And I'm going to check that unit vector, or that direction vector, from A to D. We go down 5 in the K direction, so that's right. We go minus 4 in the I direction and minus 5 in the J direction. So I feel good about that one. So now we have basically all three of our vectors. And then we know we're doing static equilibrium. So for the static equilibrium, we have the sum of the forces equals mass times acceleration. It's static equilibrium, so that mass times acceleration is 0. So we can do the sum of the forces in the x direction equals 0, sum of the forces in the y direction equals 0, and sum of the forces in the z direction equals 0. And then we've set this up pretty nicely. So we have, all the I direction vectors, J and K, and then we had one other force on our free body diagram, was that 800 Newton force going up. So I'm just going to go to the next page and sort of copy some stuff over. Alright, so I just copied those formulas over for the different vectors. So now we know something about AD, AB, and AC, and then we know this 800 Newton force that's going straight up. So now we can look at these three equations. So let's do the sum of the forces in the x direction equals 0. So the forces in the x direction, we have AB has an x component. That would be AB times 4 over the square root of 57. That's this I component here. And then the AC has an I component. So minus AC times 2 over the square root of 38. And then the AD also does, so minus AD times 4 over the square root of 66. And then that 800 Newton force doesn't have anything in the x direction, so that equals 0. And I'm going to go ahead and calculate those out. So we get 0.5298 AB minus 2 divided by the square root of 38. 0.324 AC minus, and then 4 over the square root of 66. 0.492 times AD, that equals 0. So there's one of our equations. I just multiplied everything out. Now let's do the sum of the forces in the x direction. So let's see. Sum of the forces in the y direction equals 0. So for the y direction, that's basically this one. And remember, you have to do times the AB because that goes all the way across. So we get the sum of the forces in the y direction equals 0. That equals 4 over the square root of 57 times AB plus 3 over the square root of 38 times AC minus 5 over the square root of 66 times AD. And then that 800 Newton force is only in the z direction, so those equal 0. I'm going to go ahead and multiply those out. So 4 over the square root of 57 is at 0.5298. Let's see. So I'm going to write it over here. 0.5298 AB minus 3 over the square root of 38. So 3.4867 AC minus 5 over 66 square root 0.615 AD equals 0. So that's our next equation. So we have two equations. We need one more. Fortunately, we have one more that we can do. So now we have the AD, or now we have the sum of the forces in the z direction equals 0, and that equals negative 5 over the square root of 57 AB minus 5 over the square root of 38 AC minus 5 over the square root of 66 AD. And so we'll go ahead and multiply those out. Let's see. That's negative 0.6623 AB minus 5 over the square root of 38, 0.8111 AC minus 5 over the square root of 66, which I guess that's the same as before. So that's 0.615 AD. And then we also have that 800 Newton force, which is plus, oh sorry, we should put that over here, plus 800 Newtons. So I'm putting it on that one. Let's go ahead and move that to the other side. So that equals negative 800 Newtons. That's somewhere where you could have gotten into trouble. So now we have basically 3 equations and 3 unknowns. For anyone that's taken linear systems recently, you can imagine we can pretty easily set up a matrix to solve these and use our calculator solver. So I'm just going to go on the next page and actually write that up. Alright, so now we're just going to set up some matrices so we can deal with the three equations. So if you remember this, we basically set up one matrix, and then it's times AB, AC, and AD. And then that equals, so you multiply those two, and then it equals 0, 0, negative 800 newtons. And for each of these, so basically it's 0.5298 times AB minus 0.324 times AC minus 0.492 times AD, and that equals 0. So over here. And then the next one, we have 0.5298 times AB minus 0.4867 times AC minus 0.615 times AD, and that equals 0, so that's good. And then for the third one, we get negative 0.6623 times AB minus 0.8111 times AC minus 0.615 times AD, and that equals negative 800. So we're in good shape here, it looks like, if I didn't make any more errors copying stuff over. What I'd recommend that you do now is learn how to solve these types of equations or linear equations, or sets of linear systems in your calculator. With mine, basically you have A times X equals B. And so you put in the matrix for A, you put in the matrix for B, and then you can solve for X. So I'm going to pause and do that in my calculator. I don't think any of you have an HP 48G calculator, so it won't help you if I show you on mine. But I'm just going to do this. Figure out how to do that on your calculator because it'll save you a lot of time. So as I was entering those into my calculator, I went back to the previous page just to verify I had the numbers right, and it looks like I already had one of the numbers wrong. So I'm just going to do it with this ink. So we have the AB. So that one's positive here, negative, negative. So those are the signs are right here. For the sum of the forces in the Y, we have positive, positive, and then negative. So positive, this one should be positive, and then negative. And then for the last one, it's negative, negative, negative. So I just think that that middle one was wrong. So I just wanted to show y'all that. So this should be positive, and then that would put this one as being positive. All right. Alright, so I just did the calculations in my calculator, and basically what I got was that this vector AB, AC, and AD equals 577.7, 85.8, and then 565.5. And so that means that the magnitude of AB, so the tension in AB is 578 newtons. AC equals 85.8 newtons. And AD equals 566 newtons. So good thing I caught that negative sign. If I hadn't, I would have been through all the frustration again. So make sure you just check and double check as you're going through these steps.